So I want to open by saying that my co-authors and I are truly honored to be recognized as finalists for this award. We put in countless hours of our time over the past few years working on this project, so we truly appreciate the recognition. Again, my name's Tracy Doubler. I'm the head of North American soybean breeding projects at Syngenta. So I'm a plant breeder by training. How many people have ever heard someone say that before? Probably not many, right, in this room. But this afternoon I'm going to talk to you about the genetic gain performance metric that we've developed and how we're confident that it's going to allow us to accelerate agricultural productivity. Specifically, it's going to allow us to accelerate soybean yields going forward. So I want to open with a quick introduction on why soybean as a crop is so important. So those of you in the room may or may not know that soybean is one of the major crops in the world today. But why is that? Well, the oil extracted from the soybean seed is the second most consumed oil in the world. It's second only to palm oil. That oil is used to create products such as cooking oils. It's used to create printing inks. It's used to create spray foam insulations. And it's used to create soy biodiesel. Soybean is a major ingredient in most animal feeds, especially in your fish feeds. And soybean is one of the largest sources of protein both for livestock and for humans. So soybean clearly has global economic reach. The crop is grown in numerous countries throughout the world. Its products are imported by even more countries. So globally, Syngenta is a leader in developing superior soybean varieties. So if you ask the grower, the farmer, our customer, what it means to be a superior soybean variety, they will tell you that is a soybean variety that has high yield. Growers, farmers get paid for the soybean yields that they obtain in their fields. So to the customer, to the grower, yield is the most important metric. Now beyond that, the customers have come to expect that the new varieties that we release into the marketplace today have greater genetic potential for yield than the varieties that have previously been available to them. And that amount of increase in genetic potential for yield is called genetic gain. So in the seeds industry and the plant breeding industry, genetic gain is the key performance indicator. So while let's talk about improving soybean yields, while let's talk about improving rates of genetic gain, let's tie that to the world's population. In 1950, the world's population was 2.5 billion people. By 2011, that population had grown to 7 billion people. The estimates are if we stay on this trend, by the year 2050, our population will reach 9 billion people. We're adding approximately 1 million people to the face of this earth every month. That has to have some impact on demand for food and feed. Our analysis suggests that if we stay on this path to reaching 9 billion people, in order to feed that many people by 2050, we need to double our rates of grain production over where we are today. So how have we done historically on increasing production in soybean? As an industry, we've tried to measure that increase in production year over year since about 1980. And what we found on average, we're increasing production by about 0.6 of a bushel per acre each year. And while that's a notable achievement in a crop like soybean, an inbreeding crop like soybean, the challenge is if we stay on that trend as an industry, we will fail in doubling production by 2050. We need to be on a trend that's closer to 2 bushels per acre per year to meet that increased demand. So we have some work to do. So how do we go about doing that work in Syngenta? That's the soybean variety development process. Let's talk just a little bit about that process. So within Syngenta's breeding program, we're organized into breeding teams. And each of those breeding teams is responsible for developing commercial soybean varieties that have high yields specific to a detailed geographic region. Each of those teams is headed by a highly trained plant geneticist, we call a plant breeder. That individual typically has some form of advanced degree, whether it's a master's degree or PhD. He or she is responsible for ensuring that team uses a fairly well-defined step-by-step variety development process to create and identify those high-yielding lines in our breeding program. So there are 3 phases of that process, and the sum of those phases represent one variety development cycle. So what's phase 1 of that cycle? It's new variety design, new line creation. Breeders create new lines for us to evaluate by selecting or identifying 2 high-yielding lines that already exist in the program and crossing them together, mating them together to create progeny, to create children. For each cross, the breeder creates about 200 children on average, 200 progeny on average. In 1 year in our program, and in this cycle, we generate somewhere between 5,000 to 6,000 crossing combinations. So we develop hundreds of thousands of new lines each year, that need to be evaluated. Again, that's phase 1 of that variety development cycle. Phase 2 is variety advancement through inbreeding. So basically allowing those lines that we've created to self-pollinate for a couple generations. Why do we do that? That allows the breeder the opportunity to identify the best lines from that group that are fixed for key agronomic traits. So we're talking disease resistance traits typically. It also allows us to create what we call a replicable cultivar to ensure that we have enough seed to evaluate these lines in phase 3 of this variety development cycle, variety evaluation, which consists of a series of regional yield trials grown over the period of 3 years. It's during that time that we compare and select varieties to advance each year based off of their yield in the fields. That is also the point in time where we want to be able to measure the rate of genetic gain, so change in yield, during each phase or each stage of testing. The challenge has been, to date, we haven't had a metric that's allowed us to do that before we develop this genetic gain performance metric. It's also important to know that this isn't a one and done process. Each year, breeders start a new breeding cycle to ensure that we have a continuous flow of high-yielding varieties into the marketplace. Now remember, that process takes on average 7 years, with the end result being commercial varieties that are released to the grower. At the same time, they're recycled back into the breeding program to be used as crossing parents. You can see during that time period, 6 more cycles have started. So this is a continuous process. It also shows you how big our program is. So if you think about it, our soybean development program is much like a fiber optic bundle, where each fiber represents 1 breeding cycle. Each color represents 1 set of concurrent breeding cycles from a single breeder. And the entire bundle represents the aggregate soybean breeding pipeline across Syngenta. So although maybe I've made that process sound quite simple, the reality is it's not. We need to talk a little bit about the soybean breeder's dilemma and how the soybean industry has tried to measure genetic gain to date. So what's the soybean breeder's dilemma? Here's the dilemma in theory. So breeders try to select for a visible phenotype. They try to select a high-yielding soybean line. And that phenotype that they see is a result of the genotype and the environment. So the genotype is that genetic proportion of the phenotype that can be selected for by the breeder. It's the portion of the phenotype that can be passed from the parents to its progeny. The challenge comes with this environmental piece. I think we all know the environment is unpredictable. We can't control it. The environment introduces significant error into this breeding process. That's the challenge. So here's just an example of how unpredictable environments add noise to the yield trialing signal. So this is a depiction of soybean variety yields across the state of Iowa in both 2013 and 2014. Focus in on one specific location. Let's look at the average yields of the varieties planted at this location in 2013. You'll see that on average, those varieties yielded somewhere between 40 to 45 bushels per acre that year. Fast forward 1 year, same varieties, same testing location. You might expect that the yields would be the same. What do you see? Yields in general increased by about 10 bushels per acre. 2014 was a much better testing environment than 2013. Why is that? Could be numerous things, right? Could be increased precipitation. Could be different temperatures. Could be more available nutrients. Could be a combination of all those things. We don't necessarily know. What we know is that's what poses the challenge in the plant breeding process. So here's just another example of the soybean breeder's dilemma in practice. You see here 3 sets of plants, right? Each of these sets of plants is the same variety. That's that replicable cultivar that I talked about. They should look exactly the same. Clearly they don't. The reason they don't, that's a product of the environment. Each set of plants was grown at a different location in the state of Iowa. The environment caused the differences you see in plant height. Yet again, just another example of the soybean breeder's dilemma. So if the plant breeder could adjust for environmental variation that they see within the environment, we could better understand the impact of operational decisions that we've made to improve rates of genetic gain across the breeding program. Let's talk a little about that concept of genetic gain. It's not new. It was first developed by R.E. Fisher as early as 1930. And Fisher used that concept of genetic gain to describe rules of natural selection, genetic variability, and phenotypic variability in predicting evolution. So the genetic gain equation looks like this, where the change in genetic gain is equal to the heritability of the trait being discussed times the selection differential. Remember, in soybean, if we're talking about change in genetic gain, we're talking about changes in yield. The heritability then is, again, that proportion of the phenotypic variability that's due to genetic variance. That's that portion that breeders can select for. It's that portion that can be passed from parents to their offspring. The selection differential is the difference between the base population mean, so we're talking about the mean yield for the parents used in those crossing combinations I talked about, and the mean of the lines selected for commercialization after that 7-year process occurs. So what you can see is that traditional concept of genetic gain is largely inadequate for the operational needs of the seed industry. And why is that? That traditional concept of genetic gain explicitly ignores the confounding effects of the environment. It assumes that the heritability for a complex trait like yield is known, and it's not. It can only be calculated at the end of each 7-year cycle, which is a significant problem in our plant breeding process. It cannot be used to measure genetic gain at each stage of the varietal evaluation phases, and we need to be able to do that. Finally, it cannot be applied across the aggregate of the breeding pipeline. So what the seed industry needs is an unbiased metric to measure genetic gain performance on an annual basis so we can better understand the immediate impacts of operational changes that we've made to improve rates of gain across the breeding program. We really need something similar to a radar system that allows us to look beneath the surface of our breeding programs and identify where issues might exist so we can quickly correct those issues. That's what we think the genetic gain performance metric allows us to do. So before I talk more about that metric, I first need to quickly talk about soybean markets, the impact of relative maturity on those markets, the impact of relative maturity on yield. So in soybean breeding, to the soybean breeder, relative maturity is a key trait. So key, in fact, that the North American market has been segmented by length of growing season. It's been segmented into relative maturity groups. And those relative maturity groups range from 000, that's the earliest relative maturity group found in southern Canada, to the latest relative maturity group, group 7. That's found in northern Florida. Now within those relative maturity groups, they can be further subdivided to indicate gradations within the group by adding a decimal point to the RM number. So specifically, relative maturity group 1 can range from 1.0 to 1.9. Now to align with that North American market, these relative maturity indices have been used to characterize time to maturity for each variety that's in our breeding program. Why do we do that? We do that because the historical data tells us that for each 10th of increase in relative maturity, which is just about a day, that's it, there's on average an increase of 0.6 of a bushel per acre in yield. So based off that, you can clearly see that it's important to compare yields within a specific relative maturity group. You cannot compare yields across a range of relative maturity groups. Now let's talk about development of the genetic gain performance metric. We first need to start with a brief overview of how we conduct our yield trials. What's the experimental design that we use? In our yield trials, we use an augmented lattice design. We use that design again because those field conditions are so variable at a site, it allows us to make some level of adjustment. Now within that lattice design, each experimental variety is assigned to a block. And within each block, we augment those blocks using check varieties that have similar RMs, similar relative maturities to those experimental entries. So those checks set the yield for maturity benchmarks. Now, every year in North America, we we run hundreds of these yield trials, and they're replicated across multiple environments. So remember, that yield measurement then is a function of the varietal genetics, the growing environment, and that random variation. So how do we calculate the genetic gain performance metric? We calculate that metric by adjusting yield. We adjust yield using the estimates of the environmental effects. We adjust yield for every experimental variety N with relative maturity R in year T for all experimental variety entries that are evaluated in the first, second, and third year of those regional yield trials. We make those environmental adjustments based off the check varieties that are in those experiments. We do that for every relative maturity group for every year. The environmental adjustment then is calculated using a 5-step convergence algorithm. We first set the initial year-to-year correction to 0. We estimate the expected yields of the checks. We then calculate the random variability, and we update the estimate of that year-to-year environmental correction. We then repeat steps 2 through 4 until convergence is reached. And convergence is reached when that correction term is less than 10 to the power of -3. Now I realize this is just a very quick overview of the algorithm. So if you need more detail, I would refer you to the appendices of our manuscript. Let's talk about implementation of the metric within the breeding program. So we implemented the genetic gain performance metric in 2010. And that's when Syngenta truly began to embrace the use of advanced data analytics to allow us to assist in making operational decisions to impact the rate of genetic gain within our breeding programs. We then used estimates of the environmental error from years 2006, or we developed estimates of environmental error for the years 2006 through 2014 using that genetic gain performance algorithm. We then used the weighted yield averages to evaluate annual rates of genetic gain by relative maturity group again within each regional yield trial stage of testing. So we used over 400,000 yield measurements, again, to both develop and test the algorithm. So these graphs simply show you the counts of yield estimates by maturity group by year for the years 2006 through 2014. And you can see that the number of observations isn't evenly distributed. It's not evenly distributed across relative maturity groups within a year. It's not evenly distributed across years. Why is it not evenly distributed across relative maturity groups in a year? It's because we align our yield trialing effort with the size of the market, with the size of the market opportunity. And the size of the market and market opportunity is much larger in the mid-maturity groups, groups 2 through 4, than it is in early or late relative maturity groups. Why more observations in the years after 2010? That's when, as an organization, we ensured we had enough quality data to determine what those environmental corrections should be. We then use that genetic gain performance algorithm to calculate the estimated environmental effects for each relative maturity group. So these graphs show you the estimate of effects, again, by maturity group, by year. And what you can see on average is that the estimates of effects typically were larger in the years before 2010. They were also typically larger in the later maturity groups. So in those years when the estimates of effect were smaller on average, so we're talking 2008, 11, and 10, there was no consistency in the level of effect. Sometimes they were positive, sometimes they were negative. In those years where the estimates of effect were larger on average, so we're talking 2006, 2009, 13, and 14, there seemed to be more consistency in the estimates. They were either consistently positive across the range of maturity groups or consistently negative, as in 2014. So 2007 was kind of our anomaly year, right? Things were all over the board this year. But what we saw were basically large estimates effects in the mid-maturity groups, and they were typically negative. So let's talk about the results. So we're talking about determining rates of genetic gain after we made the yield adjustments using the genetic gain performance metric. Let's talk about the results that we saw in stage 1, that first year of that variety evaluation process. We saw on average, before 2010, across all relative maturity groups, genetic gain was just fluctuated. It was all over the board. Extreme fluctuations. After 2010, regardless of maturity group, we saw increased rates of genetic gain. That acceleration was much more pronounced in the later maturity groups, so relative maturity groups 4 through 7. A little less pronounced in the early maturity groups, groups 1 through 3. How about stage 2, the second year of that variety evaluation process? Basically, we saw the same thing. Erratic rates of genetic gain before 2009 across all relative maturity groups. More consistent rates of gain after 2010. We saw steady rates of genetic gain in relative maturity groups 1, 2, and 3 this time. And somewhat more erratic, but still positive rates of gain in the later maturity groups, relative maturities 4 and 5. So how about stage 3? Now that's the third and final year of that yield trial evaluation phase. It's the key year. Why? Because the lines that perform well in this third year are advanced for commercialization. That's what we're going to sell to the grower. So we need to ensure that we're making gain here to be successful. What do we see? Basically, again, we saw the same thing. Before 2009, extreme fluctuations in rates of gain regardless of relative maturity group analyzed. After 2011, as we saw before, consistent rates in genetic gain improvement across all relative maturity groups. You also see here that we had a gap in 2010. That's because our breeding program was going through a GM trait transition. We simply didn't have enough quality observations to determine our rate of genetic gain that year. So what are the conclusions? What are our takeaways? Before implementation of this metric, we were unable to calculate genetic gain contributions to yield at each stage of testing, and we needed to be able to do that. After implementation of the metric, we were able to track progress each year and intervene with operational improvements as needed. The improvements to the operational decision-making process resulted in genetic contributions to yield in North America that range from 1.6 to 2.4 bushels per acre per year. So again, it was not the metric that allowed us to have these improvements, it's the operational changes that we made. The metric allowed us to measure the impact of those changes. The important thing is, after all this work, we are now on that 2 bushel per acre per year trajectory that we need to be on to increase soybean yields to meet demand of that 9 billion, the population of 9 billion people in 2050. So Syngenta's estimated genetic gains are now 40% greater than the gains seen before implementation of the metric in 2010. Without the genetic gain performance metric to guide us, and again, guide us, Syngenta would have needed to invest an additional $250 million, probably in yield trials, to achieve the same 40% improvement in genetic gain. So while the primary contribution of the genetic gain performance metric to agriculture is truly based on operations research, it's lived out in the revolutionary nature of the results. It's allowed us to increase gain within our program. We truly believe that's going to allow us to feed a growing population. So with that, I need to thank the co-authors, Joe Byram, Craig Davis, Greg Doonan, Vaughn Castor, Ron Mowers, all from Syngenta, Bill Beavis from Iowa State University, Sam Perry from Arizona State University, Jack Klober from Chromite for critical evaluation of this project. Appreciate all that. Without their efforts, I promise you, we wouldn't have been successful with this project. So with that, I appreciate your time this afternoon. Be happy to answer any questions you might have.